All right, so we are starting chapter 10, which is antimicrobial treatments. So antimicrobial refers to treatments that work against all types of microorganisms. We're mainly going to be focusing on antibiotics in this chapter, but we'll start out by talking kind of very broadly about all antimicrobial drugs. So, first off, how did we get here? So, antimicrobial drugs have been available for like the last 70 to 80 years. And they really have saved countless of lives and dramatically changed the way that we approach infection control. So, if you think about it, what happened in the olden days, let's say, in days past, just a simple scratch or a cut that gets infected could turn life-threatening and you could die from it. If you think about during the Spanish American and Mexican Wars, about 7 times as many soldiers died from wound infections or from diseases than from those who actually died on the battlefield. So 7 times as many. So they died from just cuts and from infections more so than dying on the battlefield because of a gunshot wound or something. So in 1928, a physician who is well known in the circles of microbiology is Alexander Fleming. So he noticed that a culture of Staphylococcus aureus was contaminated with a mold, and he saw that the bacteria, the Staphylococcus aureus bacteria that he was trying to grow, was not able to grow anywhere near the mold. So he, he determined that the mold actually excreted a compound that inhibited the growth of the bacteria. And this chemical he called penicillin, and he called it penicillin because that was the name of the species of the mold that was growing on the plate. So that's how we got penicillin today. So from 1928 until the 1940s was when penicillin was first kind of mass produced and available for everybody. Now, most non-viral infections are usually curable now because we are able to use these what we call antibiotics. All right, and that started back in 1928 with Alexander Fleming's discovery. Now, unfortunately, antimicrobial resistance is on the rise, and therefore we have this kind of ongoing research for discovering new drugs that work against these microorganisms that have become resistant to our well-known antibiotics. And so this has kind of evolved because we use a lot of antimicrobial drugs in animal foods, and there has been a lot of over-prescribing of drugs, and this has all helped to promote the evolution of antimicrobial resistant pathogens. So the Center for Disease Control estimates that about 70% of healthcare acquired bacterial pathogens are resistant to one or more antibacterial drugs nowadays. So 70%, all right, of these microorganisms are resistant to our antibacterial drugs. And so you're probably familiar with methicillin-resistant Staphylococcus aureus, or what we call MRSA. And so this threat actually emerged back in the 1960s was when MRSA was first identified. And now it's fairly common. Everybody kind of knows about MRSA now. Excuse me. So antimicrobial drugs are very specific in how they work against a microbe. These drugs can exhibit a spectrum of activity. So we use the term broad spectrum and narrow spectrum. So broad spectrum drugs are effective against gram-negative and gram-positive cells. So I have up here the example of tetracycline as an example of a broad spectrum drug. So it's effective against one or more a group of bacteria. I apologize, my dog is scratching her ear in the background, and that's what you're hearing there. And then we have narrow spectrum drugs. So narrow spectrum drugs target a limited range of bacteria. So vancomycin and bacitracin are effective against just gram-positive cells. So they target just a specific group versus the broad spectrum, which target many different types of bacteria. So gram-positive or gram-negative, or narrow spectrum, which you only have one group that's being targeted. Now, typically narrow spectrum are preferred because they don't affect your normal microbiota as much as a broad spectrum, right? So if it's broad, it could be also killing off your microbiome, right? So the organisms that live in your stomach or in your intestines, when you take that antibiotic, they could be killed off by a broad spectrum as well. So narrow spectrum are much more preferred, but in order to prescribe a narrow spectrum, the physician needs to have a very good idea of the pathogen that's causing the problem. And so that can be a problem to immediately be able to prescribe a narrow spectrum. All right, so we have some terminology here that we want to kind of get out of the way first. So we have the term prophylaxis at the top there. So it says this is the use of a drug to prevent infection of a person at risk. All right, so prophylaxis is simply the use of a drug. So if you've got somebody who has been exposed to some type of microorganism and they are not showing any signs or symptoms yet, you may want to go ahead and give them the drug because they're likely to develop an infection and you want to get on top of it first. So prophylaxis. So antimicrobial chemotherapy, so that's simply the use of drugs to control infections, and this could be any type of infection that we're talking about. And so therefore we're using the term antimicrobial, so this could include bacteria, includes fungi, could be the worms that we were talking about, the helminths, so anything. As it says, it's an all-inclusive term. Now, more specifically for this chapter, we're really going to be targeting antibiotics, all right? So as it says, it's a natural substance. So once again, initially we identified antibiotics coming from fungi with Alexander Fleming. So it says in the term there, substances produced by natural metabolic processes of some microorganisms that can inhibit or destroy other microorganisms. So it's very general there, but then it says the term is used for drugs targeting bacteria and not other types of microbes. So generally we're talking about medicine that is used to target bacteria, all right? So we talk about antibiotics as being effective against bacteria, but not effective against viruses. All right, so now we get down to our different types of drugs. All right, we want to talk about semi-synthetic and synthetic, and we've already talked about our narrow and our broad spectrum. So with penicillin, all right, so many researchers began to investigate a lot of the naturally occurring antimicrobial agents. So therefore, our kind of stash of antibiotics started to grow and become more abundant as we started to look about, and we found that there are a lot of microorganisms that are secreting different substances. And so we developed our arsenal of antibiotics. Now, we do have what we call synthetic antimicrobials, and these are manufactured by a chemical process, right? So in addition to the naturally occurring ones, we also came up with some of our own. So this is one way to kind of help overcome antimicrobial, resistance. All right. So when we come across bacteria that are resistant to our well-known antibiotics, they have come up with synthetic versions that these organisms so far have not become resistant to. All right. So this is chemicals that are developed solely in the lab. And therefore, this takes a long time, though. So from research and the mass development, and therefore from mass development and then getting it onto the shelves takes a very long time, right? Especially to get it passed and approved by all the government agencies. So it takes a long time to do that. Now, drugs don't need to necessarily be built from scratch like our synthetic versions. We can have semi-synthetic versions, which are naturally occurring antibiotics that can be chemically modified to improve their action or to make them more stable. So these are semi-synthetic. So researchers basically kind of modify just a part of the chemical structure. So they might add something to the chemical structure, or they might just tweak part of the molecule, and therefore we would consider it to be semi-synthetic. So, right, with penicillin, when that was discovered, we now have ampicillin and amoxicillin. And these are two semi-synthetic antimicrobials that were derived from penicillin. So ampicillin and amoxicillin are semi-synthetic. Now, characteristics of an ideal antimicrobial drug. So if we're going to develop a new drug, they must possess a number of properties. So the core principle of antimicrobial development is that the drug must exhibit what we call selective toxicity, meaning that it inhibits or kills the targeted microorganism without damaging the host cells, right? You don't want your body to be harmed when you take this medicine. So this is one feature that sets antimicrobials apart from when we were talking about disinfectants. So disinfectant like bleach is not selectively toxic. It might effectively eliminate the pathogen, but it could also damage your cells. So another property that matters with a candidate is how it's administered. So oral administration is preferred since it's easiest. Orally administering drugs must be stable in the acidic environment of your stomach, and they have to be able to withstand the digestive enzymes. And it also has to be absorbed by your body, though. So it has to be sufficiently absorbed by the intestines in order to reach what we call a therapeutic dose. And then we have to worry about the kidneys and the liver, because these are key organs that metabolize and eliminate drugs. So they may be susceptible to damage by certain drugs. So we know that aminoglycosides are known to affect the kidneys. And many times once the drug is discontinued, though, at least the symptoms tend to resolve, right? So any symptoms that you may be feeling because of taking that drug a lot of times go away after you've discontinued the use of the drug. So we also need to consider the length of time that the drug remains active in the body. So a drug's half-life is the time it takes for half of the dose to be eliminated or deactivated by the body, often by the kidneys or the liver. So azithromycin has a half-life of up to 60 to 80 hours. So a drug with a long half-life doesn't need to be taken as frequently to maintain a therapeutic level in the body. And that's why some antimicrobials must be taken 3 times a day, while others may be taken only once a day. And we also want them to have few side effects and no adverse interactions with other drugs that patients might be taking. All right, so kind of